Hello everyone, my name is Saurabh Kumar. Now I am going to explain the question that I have taken in transport phenomena assignment. So we will see first question. The question says a Newtonian fluid is flowing in a laminar flow through a narrow slit formed by two parallel plates separated by a distance 2b. One of the plates moves with a velocity v0 while the other is stationary. The flow is driven by pressure difference between the inlet and outlet represented using modified pressure. Calculate the shear stress distribution, the velocity distribution, and draw carefully labeled sketch of this function. So now we will see its solution. So first we have to analyze that how velocity is changing. So we can see in the slit that there is only velocity in z direction. There is no velocity in x direction, there is no velocity in y direction, and the velocity is not changing in z direction because of fully flow or continuity equation, and the velocity is not changing in y direction because end effects are neglected, and now the velocity is also only changing in x direction. So here we can see that velocity is only changing in z direction, and now we can see the pressure is also only changing in z direction. This is our z direction, this is y direction, and this is x direction, this is y direction, this is x direction. So what is given information we can take out first. So two parallel plates separated by 2b, one plate at minus b is stationary and another at plus b. So one plate is at here we can see in the diagram, one plate is at we can take here first we have to find the origin. So origin will be there, so it will be plus b and minus b. So the minus so we have taken what we have taken that plus b moving with velocity v naught, and the velocity is driven by pressure difference p naught and p0 and pl. P0 is at z is equal to 0 and pl is at z is equal to l. Now we have to do the cell balance. So first we have to take the differential cell. So the dimension of the differential cell will be WLX. Why? Because our velocity is only changing in x direction. So our dimension will look like a cuboid, and its dimension will be WLDX. Now we will balance the momentum in z direction. Okay, so rate of z momentum into the cell at z is equal to 0 is equal to area perpendicular to z, that is w into delta x. W into delta x, look there, w into delta x into phi zz. The moment that is coming in z direction is phi zz, and is at z is equal to 0, and rate of z momentum similarly rate of z momentum out of the cell at z is equal to L, w delta x its area, and phi z at z is equal to L. So this, and rate of z momentum into the cell at x is equal to z momentum in x direction. So now x direction, z momentum x direction, so which this is the direction, so its area, what will be area, w into L. Similarly out at x plus delta x will be this. So we write the momentum balance, rate in minus rate out plus gravity is equal to 0. Now we put the value and we divide by WL delta x and multiply by minus 1. So this equation will come, and this is the definition of derivative. So we write in derivative form. Now we will find the value of phi xz and phi zz. So we can see here that phi ij is equal to rho pressure into rho ij plus rho ij plus tau ij. So here we can say that velocity is only in z direction, so we can only take this term will be 0. So here we can say that phi zz will be p plus rho v square, and phi xz which will be tau xz, and rho v z square, as z is not changing, so input and output will be same. So our final equation, and substituting pz is equal to pz minus rho g h. So after substituting everything in the above equation, our equation will look like that. So now we will integrate to get the profile of this tau with x. So first we do this and integrate. So using viscosity, so this is now tau xz is equal to mu vz by dx. So here we will apply the boundary condition. What boundary condition we will apply? That at here we will apply the boundary condition. So here applying the boundary condition, here we will find the first constant, and that constant will come out minus mu v naught by 2b. So here we can see which boundary condition we have applied. So here we have, how many boundary condition we have? 1 2 3 4 boundary condition we have taken. So at x is equal to, at x is equal to b, at x is equal to b, our tau is equal to 0. So this will come out to this equation. Now putting the value of constant, our final stress term will come out. Now we have to find the velocity distribution. So using the again differentiating the this value, and here we have left the mu. So first we will copy that. So the dividing by mu, we can find that, and integrating again, and then again constant. So using this boundary condition, we can find the velocity profile. So this is velocity profile, this will come, and when we plot this, so this is stress versus slit width, and this is first in the fluid in contact with stationary slit will be 0, and the fluid in contact with moving will not be 0, and the maximum velocity will come somewhere not in between but near the moving slit. So this type of a distribution will come. Now we will move to the second question. The second question, what it says: a Newtonian fluid flow through a circular pipe of radius 5 mm under a laminar condition. The pressure drop across a pipe length of 2 meters is 400 Pascal. The viscosity of a fluid is this much. Derive the expression for the velocity profile in cylindrical coordinates. Calculate the maximum velocity of the fluid. Calculate the average velocity. Determine the ratio of average velocity. So we will see this, how we have done this. So here is given data, and here is assumption. Now using Navier-Stokes for fully developed flow, putting the value, rearranging this, and multiplying by r, integrating once, dividing by r. So here we can say that here we get that equation. So look this equation very carefully. So here we can see that at r is equal to 0, there should be some finite value of velocity. So this term should be 0. So here you can see that 0. Then again we integrate again, and here we can get C2. Now applying that, at r is equal to r, v is equal to 0. At boundary condition we have taken that r is equal to 0, the molecule molecule in contact with the surface is 0. So we find the value of C2, and the final velocity profile here comes out to be this much. So this is velocity profile, so this is velocity profile. See, now maximum velocity profile will be this much. Now V max, so V max is this. So after putting the all value, we have find the V max. Now average. So how to calculate average velocity? So we will see here in a cylindrical system how to calculate average velocity. So V max है V average is equal to V by what is the definition of V average? V average will be flow rate upon area. Velocity, what will be velocity? Flow rate upon area. So here will be Vz. So Vz we will take what Vz we have got. Look there, what Vz we have got. Vz is a del P 4 mu r square by r, and what will be its corresponding area? So we integrate 0 to 2 pi and 0 to r dr theta divided by r dr theta. So doing this, and we have put this value there. So it's come to 1 by 2 Vz max. So here we can see that calculating when you all put the value means what is the average flow rate area will be total flow rate by area. So we will put this value and multiply by area and divide by area and divide by area. When we integrate that, our average velocity will become by 1 by 2, and ratio of average and max velocity will be 1 by 2. Now we will see to question number 3, pipe flow with gravity. So now we will jump to question number 3. What it says? Question number 3: a Newtonian fluid flows through a circular pipe of radius 6 millimeter inclined at angle of 30 degree to the horizontal. Now it is not horizontal, it is vertical inclined pipe. The pressure difference between 2 points 2 meter apart is 500 pascal. The fluid has viscosity of this much and density this. Derive the velocity profile considering gravity. Calculate the maximum velocity. Determine whether gravity assists or oppose the flow. So same type of question we will see. So here pipe flow with gravity, given data is this much, velocity profile with gravity, affecting gravity. So this is come from cell momentum balance. This come from cell momentum balance. We will quickly see that how it's come. So here we can say that first we have to take the differential cell, this type of cell, and the velocity is only changing in z direction. So we will take the only z momentum, and after substituting all these value and doing the differentiation and this value and putting the value of phi rz and phi zz, so our final term will come like this: p naught minus and the putting the value of gravity also we can see here. So the shear stress is this much. Okay, so shear stress will come like that, g sin theta. Here you can see that our z is this, del here is del p by l minus so here is so this is the same here. G rho g sin theta is not substituted with that, and Okay, so this is no, here look, here is the del p by del z. What will be del p by del z? So this will be our del p by del z. So now our v rz profile will be this by doing cell momentum balance, and maximum velocity similarly at r is equal to, where will be maximum velocity at r is equal to 0. So putting r is equal to 0, this will be r square, and del p by l this much, and v max will be that. So maximum velocity this should be, because that much shear stress it will calculate. So now we will see how this vz by vz r is equal to this term came. So here look, so here we have taken cell momentum balanced. Okay, now we have got the, after substituting all the value phi rz, phi zz, this is the similar problem, you can go through it. And now here the tau will be that, and for velocity we have to put the value of mu, and there we will get the v. So v will be this, and putting the boundary condition it will become this. So it is same as you can see that we have derived here. So here only difference is p0 minus pl. So here it is not g, pg sin theta is there. So we will put it there and we will solve it. Now question number 4. Now question number 4, we will quickly see it. Newtonian fluid flow through a slit. Under laminar condition flow, the length of the slit is 1 meter and the pressure drop across the slit is unknown. So we have to calculate the pressure drop. The maximum allowable shear stress at the wall is 10 Pascal. The viscosity of the fluid is 0.001 Pascal. Determine the maximum allowable pressure difference, maximum volumetric flow rate, maximum velocity. So we have to find every maximum. So we will quickly see it, what is happening. So in question number 4, given data is width and that much, pressure gradient will be pressure gradient, what will we have to calculate. So for slit we have derived in the very first question how it is varying. So here you can say that this tau xz is equal to mu vz by dx. So similarly here will become that term, and we will put that, and we have to find the del p, and every rest value is given. So here we will get the del p this much, and what will be flow rate. So flow rate, for flow rate, so for flow rate it will be velocity into area. So what is velocity? So in the first question we have derived the velocity, and for velocity for non-moving, here in this question both the slit are stationary. So stationary case, the velocity equation comes, when you solve it, the velocity will come like this. Oh wait, velocity will be velocity into area. So we have to find the maximum velocity. So maximum velocity, where it will be maximum velocity at x is equal to velocity profile. Okay, wait. This is the tau, and when we differentiate with, so velocity is, and after putting the C2 we have velocity this. Okay, so where will be velocity at the max velocity? First question, velocity will be max at del P by mu. Okay, so we have to differentiate that, and when we differentiate that, it will come V max this, and after putting value we will find this value.